Do you have any questions related to maybe some week 6 or 7?
Sir, yes, sir. We have a questions about week 6.
Okay, so what is your question?
Sir, can you explain about basis and span?
Okay, so okay, then first I have to explain about span, then only I can talk about basis. So like my question is, have you watched the last session videos?
No, sir.
Okay, like then I will suggest you to watch the last session video, like because as far as I know, Subhajit explained it properly. So
Okay, sir.
okay, so like, but yeah, you watch it. Okay, so if
Okay.
still you have problem, you please come and ask. Okay, because
Okay.
it's yeah. So the point is, it's a serious thing. So I'll suggest now you go and watch it. Okay, so
Okay.
and you come back and ask in this particular live session. You come and ask. Okay,
Okay,
I will
sir.
try to explain it again. Okay.
Yes, sir. Sure. When was the previous live happened?
Last live session, maybe it happened Friday.
Okay, sir.
All the
Okay.
sessions are displayed in the Google calendars.
Yeah. You can check it.
Okay, sir. Okay. Yeah. Thank you. Thank you.
Please, now you please go and watch it. And if you have
Okay, sir.
doubt,
Okay.
you come and ask it.
Yes. Okay.
Okay.
Sir, I had a doubt regarding linear mapping. Can you please explain the topic linear mapping of linear mapping?
Okay, linear mapping. Like, do you want me to explain you
From the start, sir?
From the scratch.
Yeah.
Okay. Let me. Okay, I'll share the screen. Okay, I'll start explaining.
Sir, and one more question. I'm struggling with the maths 2 component of this semester. So what shall I do? Because it is taking me a longer time to understand the concepts.
Can I know your name?
Sir, it's Sudhanva, sir.
Okay, so the problem. Okay, this is I will say this is quite normal, because the problem is it's completely my suggestion, like my not suggestion, it's my opinion. The problem is with the syllabus. Okay, so like it's huge. Okay, so because in 12 weeks you are learning calculus, linear algebra, and multiple calculus. So yeah, so I don't think it will be easy. So one thing I will suggest you to solve problem. Like the thing is, you have to do a lot of work. Then only probably you can can manage the things.
Sir, yes, sir. I'm solving the practice assignments. But the problem with the practice assignment is that if we click on the check answers button, it only checks our answers and not gives us the solution.
Solutions is certainly, see, the solution we are not giving it with the release, the weekly content, right? The thing is, we are giving you some time to solve. Okay, first you try all the questions, then after that we are providing you the complete solution. Okay, see, if at the time itself, like when we are providing you question, and at that time also, if we will provide you the solution, then believe me, you will not learn anything. You will, within some days you will forget whatever you have done by looking at the solution. Okay, so you will face the problem in the quiz and in the semester. Okay, so but first I will suggest you try to solve activity questions. Okay, so but for activity question, you can get most of the solution in discourse. Okay, so have you joined discourse? Hello,
sir, which course, sir?
Discourse.
No, sir. What is it?
It's a forum where you can join. If you click right side forum, right, in the course page, it will take you to discourse.
Okay, I'll suggest you to explore that forum, because many people, they are actually using it. Okay, and if you post your doubt, some of the student will come and solve it. Okay, like rarely we go and solve it. Just one of your friend will come and solve your problem. So I will suggest you use discourse. Okay, so so the problem is we cannot provide you the solution like for activity question, because it's like some 50-60 questions are there. So it's difficult for us to write all the solution and give it to you completely, because see previously we didn't want to provide you the solution, but now I feel okay, like some of you are struggling to do like to understand the concept, but the problem is the number of questions in the activity part is huge, so it's difficult for us to give you the complete solution. But as I said, like in this course you will get solution of almost all the questions, activity questions. Okay, and certainly we are actually providing you the solutions of practice assignment and graded assignment.
Yes, sir. I'll see to it that I join.
Okay, so who asked me to explain the concept of linear transformation?
Sir, me only, sir.
Okay, let me start. So you are familiar with the concept of basis, dimension, all these things, right?
Yes, sir. Yes, sir.
Okay, fine. Okay, so can you see my screen?
Yes, sir.
So the first thing is basically what, linear transformation. So, so the first thing is linear transformation. So one of the thing when you are actually studying some objects, the most important part of that study is basically some particular kind of maps from one object to another object. So here, what is your object? So in this particular linear algebra course, what is your object? You are trying to study the vector space, right?
Yes, sir.
So linear transformation is basically a map from a vector space to some another vector space, and that maps also satisfy some property. It preserves some property in some sense. Okay, it preserves the addition and it preserves the multiplication, scalar multiplication. Okay, so what is the definition of that linear transformation? So linear transformation. So what we define linear transformation from a vector space to some another vector space. Okay, so suppose I have a map that is T, which is from one vector space V1. So V1 is a vector space, and this is from V1 to V2, and V2 is another vector space. So this is a map. So when I will call it this map to be a linear transformation, if it satisfies two conditions. So what are these conditions? The first condition is T of V plus W is equals to T of V plus T of W. So in some sense, you can see it's preserved the addition structure. Okay, so if you are adding two elements, the image of that element is basically sum of their individual image. So image of this is sum of individual image.
Sir, but here T is a function, no?
T is a function. Yeah.
So how are like this seems a bit weird to me that
no, the thing is no, if you take any function, they may not satisfy this condition. That's why we are saying this linear transformation, not a function. Okay, because we are putting to extra condition. Okay, see, if I will take this particular function, okay, from x to so this function is basically from R to R, right? So I defined it like this: x goes to x square. So now you can see this particular function this particular function doesn't satisfy the first condition, because if you take f of 1 plus 1, you are getting 4, which is not equal to f of 1 plus f of 1, which is 2. So this particular condition, this is not additive. Doesn't satisfy the condition. So I'm not saying all the function will satisfy this first condition. Okay, what I am saying, if a function satisfies the first condition and some another condition, then I can say that that function is a linear transformation. Okay, I'm not saying all the function will satisfy this condition. Like you can see, this particular function is not satisfying the first condition, right?
Yes, sir.
Hello. So this is not a linear, like this. You cannot say that f is a linear transformation. So I'm not saying all the function will. There are so many functions which are not linear transformation. Okay, you got my point, right?
Yes, sir. Yes, sir.
Okay. So yeah, this is my
Will there be any solve with instructor session?
today. Hello.
Yes, sir.
Actually, okay. So the thing is, see, the problem is in this week particularly, so many people, like in this linear algebra course, actually, so many people are facing the problem. Okay, so that's why actually I'm first trying to explain you the concept. Like if you are facing some problem with the concept, then first I'm trying to explain you. If I'll have some time, then probably I will give you some question to solve. Okay.
So this is with respect to week 7, right?
Probably I don't know. Like maybe week 6 or week 7. Like I have no idea.
I think it
This
should be
this is for
week 8, I think.
No, this is
No,
certainly
sir.
not week, not week
No,
8.
week 8 to just now released.
Okay.
This is related to week 7.
Okay.
The last 2 video is based on mapping and transformation.
Okay, that is fine. But yeah, you can ask from week 6 also. Okay, let me explain you this linear transformation concept first. After that, we can decide. So, okay, so the thing is, so whoever asked this question, are you listening?
Yes, sir. I am.
Okay, so the first condition is this. So you have a map, so it should satisfy this condition. And the second condition, so you know V1 is a vector space, V1 and V2. They are vector spaces over your real number, right? So the scalars, they are coming from the set of real number. So it should satisfy the next condition. So this is true. So the first condition, this is true for all V and W in your V1. That is the domain set. And the second condition is it should satisfy, it should not satisfy, it should preserve the multiplicative structure. So that what is that? That is T C comma V is C into T of V for all C in your field of real number, and for all V in your vector space V1. Okay, in some sense, if you are multiplying with a vector and whatever value you will get, you take you multiply C with the image of that vector. Okay, that they should match, right? So the definition is clear. Hello.
Yes, sir. Yes, sir.
So I'll try to explain you with some example, like how. So suppose you are given with a map. So how you will check whether that particular map is a linear transformation or not. Okay. So let's start with the basic example. Okay. So can you tell me what can be example of a linear transformation? Some very trivial example.
Sir, X maps to X.
Even that is, I will say that is also not trivial. So the first thing should come into the mind is the zero map. You define a map from set of real number to real number, and T of X is 0 for all X.
Yes, sir. Yes, sir. Got it.
In R. So now you can check that this map satisfy all the property, because yeah, so the value of the image for all the elements is 0.
Sir, this is not 1-1, right?
No, but sorry, but I don't need 1-1 condition for a linear transformation. What I said, linear transformation is a map from V1 to Vn, and it should satisfy this condition, right? But I never mentioned that this map should be 1-1 or 1-2. Okay, that is extra condition. Okay.
Yes, sir, that is isomorphism.
That no, 1-1 doesn't imply isomorphism. 1-1 and on 2 implies isomorphism. Okay, so I'm not talking about this. I will talk later. So the thing is, so my first question is, okay, the first thing is T is a linear map from a vector space V1 to V2 if it satisfies these two conditions. Okay, I am not putting any extra condition, whether T is 1-1 or 1-2 or whatever. I am not putting any other thing. I'm just saying that if they satisfy these two conditions, then you can say that T is linear transformation. So for this particular example, I need to check whether this particular example satisfy these two conditions or not, right?
Yes,
Hello?
sir. Yes.
Okay. So what
It is not, if X tends to R, why it is not?
Sorry, I can't hear you.
If X tends to R, if X is mapped to X, then why it is not a vector space?
No. It's a linear transformation. But what I'm giving example of this. I'll come to that example. So what I asked him, give me a very trivial example. Okay. So that is what. So the zero map, in some sense, is much more trivial than whatever you said. Okay, that's what I said. I'm not saying that the map from this particular map. I'm not saying that T from R to R, that is basically the identity map, is not a linear transformation. I'm not saying that.
Okay.
Okay, and this is a linear transformation. So as you can see, if you check T of X plus Y. So we want to know whether T of X plus Y is equals to T of X plus T of Y or not. That is first condition, right?
Yes, sir.
So what is T of X plus Y? What is this value? So for this particular linear transformation, what is T of X plus Y? Hello?
It will be 0, no, sir?
No, whoever asked this question, I'm asking to him. Okay, so.
Sir, but we haven't defined anything for X plus Y, and we don't also know Y and X. How can we say it?
No, what I defined? I defined T of X is equal to 0 for all X in R, right? You take any real number, okay?
Okay, sir. It will be 0 then.
0. So now what is X? X is a real number. Y is a real number, right? When you are adding two real number, you will get another real number, right?
Yes, sir.
So then T of X plus Y should be 0, right?
Yes, sir. But for all X belongs to R, but we haven't mentioned that for X and Y belongs to R. So, but Y we have introduced here itself now. So how can we say that T of X plus Y is equal to 0?
No, I see the thing is, okay. So this is a map. Okay, this is a map. What is the domain of this map? R, right?
Yes, sir.
So when I'm writing, so okay, so you want me to write it even more precisely. Okay, so as you can see, this should satisfy for all V and W in V1, right? So okay, so let me start with okay, so let x and y belongs to R. So what we need to check? We need to check T of x plus y, whether T satisfy this condition or not. So now can you say what will be the value of T of x plus y?
Yes, sir. It will be 0 and it will satisfy both the conditions.
So this is 0 and this is also 0.
Yes, sir. Yes, sir.
This is 0. So then the first condition holds for this particular linear transformation, right?
Yes, sir.
So next you need to check the second condition.
Sir, it will also be 0, sir.
Because x is a real number, c is a real number. So see, the same method you can apply everywhere. So why I'm repeating this trivial thing, because sometimes you have to realize what is going on this thing. So whatever actually example we have given you in activity question, you can do it using the same thing. Like it's the same thing you are doing for each and every map. So this should be equal to T into. So since C is in R and X is in R, T of Cx is in R. Cx is in R. That's why by definition it is 0. And similarly, this is 0 and C is in R. So if I multiply with C, I will get R. 0. So this is also true. This is also true for all x, y in R and for all C in R. So this map is a linear transformation. So similarly, you can do it. So can you do it if so? So similarly, you can check, right, for this map. So can you say that this is a linear transformation? Can you check it? Hello.
Yes, sir. Yes, sir. Yes, sir. We can say, sir.
This is basically the identity map. So okay. So next question is, you take a map R to R, and what is my map? T of x goes to 5x. So can you say that whether this is a linear transformation? Can you check it now and tell me?
Yes, sir.
So like so what is your answer? Whether this is a linear transformation or not?
Sir, it will be a linear transformation.
Okay, so okay, why? Can you tell me quickly? So T of
Sir,
x,
because it is the same example.
yeah, okay, let me, no, this is not the same example. It's a multiplication is there. So
The 5 is C now here. So
okay, so we need to check two conditions. Okay. So like, see, the thing is, don't give some vague answer. It's better if you always try to go with the definition, at least in the beginning. Okay, so once you are fine with the concept, you can say it, like you can say it vaguely, because so in the beginning you should always try to go with the definition and try to write it properly. Okay, then only you can understand the concept behind everything. Okay, so what is this?
sir, it is the first condition.
Yeah, what is this? What is the value? Yeah, this, we need to check this condition, this first condition for this map, right? Okay, so my question is, I need to check whether these two things are equal or not. T of x plus y, whether this is equal to T of x plus T of y or not. So my question is, what is this? What is the value of T of x plus y?
Sir, it would be T of x is equal to 5x.
No,
Because
I am asking what is the value of T of x plus y? What is the value of this thing?
5 times x plus y.
5 times x plus y. That is the definition, right? X goes to 5x, then x plus y should go to 5x plus y, right? So my question is whether this particular value is whether this is equals to this or not. So what is t of x? T of x is 5x. And what is t of y? That is 5y. So this is 5. You can take, since you are in a vector space, you can use the property of like you can use that distributive property. So this is, so this linear transformation satisfy the first condition. Okay, see, again I am repeating, you are doing the same thing for all the linear transformation. Okay, so that's why it's really important to know the process. Okay, so that's why I'm doing that this trivial calculation also. So the next thing is what you need to check. C of V is C times T of V. So my question is, what is, so we need to check this one. Okay, then only, so we already checked the first condition. So this map satisfy the first condition. If this map satisfy the second condition, then we can say that this map is a linear transformation. Okay, so let's check the second question. So what is the value of T of CV? Hello?
Sir, it would be 5x, sir.
T of CV. What is the value of T of Y? Hello? Hello?
T of y, T of y.
Five,
No,
5y, sir.
Oh, no, whoever asked this question, you please answer. Like, see, the problem is you are doing it for the first time, so it's completely fine if you are doing mistake. Okay, I also did the same mistake whatever you are doing now. So if you interact, then only I can explain you properly. Okay, so you don't yeah, so always try to give answer. It doesn't matter whether it's correct or wrong. Okay.
Sir, it would be 5y, sir.
T of y is
5y.
5y. So my question is, what will be the value of T of CV?
5cv.
Exactly. That is, see what is, see, if x is sorry, the image of x is 5x. Okay. So here your x is CV. So that's why you have to multiply the value of x with 5. So what I am doing, I'm multiplying CV with 5. That's why that is the definition, right? X goes to 5x. Okay. So so this is equals to 5 CV, right?
Yes,
And what is the value of T of V?
5tv.
This T of
That's
V value.
c into 5tv.
Yes.
Sorry, c into 5v.
5b, yeah. So again, similarly, you can use the property like because you have something called a comma b. Sorry, this property is there in vector space, which is a comma b, which you can write b a b. So the thing is, yeah, it's the whole thing works in a axiomatic system. So that is, it maybe it seems trivial because c is a real number, 5 is a real number, and I can multiply. But okay, these things are also going in the backside simultaneously. Okay, so this is c into 5p, which is basically 5 cp. So that's why. So this particular linear transformation satisfy all the two conditions. Okay, so that's why this is a linear transformation. Similarly, you can check, like, instead of 5, you can take some other thing. Okay, like maybe you can take R to R, and I'm not going to check this one. You can take any some x into some 7x, or maybe some 2x, whatever. Like, you take any real number and multiply with x. You will get a linear transformation. So this is a different linear transformation. So this is t, this is t dash, and t dash is what? T dash takes x to 2x, and some another is x to maybe some, you take 100x, whatever. They all are linear transformation. So these are some kind of example I gave from linear transformation from R to R. Okay, now let's so is it still so is it clear now whatever I
Yes,
said?
sir. Yes, sir. It is clear.
Okay, so so now you take some another thing, and others whoever actually listening, like listening to this, you can also ask your question, like whatever I'm explaining you right now, you can ask from there. Okay. So if you have some doubt related to whatever I said, you can ask at that time. So so okay, so R square is also a vector space, right? And R is also a vector space. So I can define some map from R square to R. Right? So this is my map. This is a map from R square to R. So I want to know whether T is a linear transformation or not. So first, what I need to check? I need to check the first condition. That is T of x plus y.
T of x plus T of y.
T of y. That is the first condition. So as you can see here, the elements, so can you tell me what so the form of an element in R square, what will be the form of an element in R square? What it looks like? It's a tuple, right?
Yes, sir. Two elements separated by comma.
Yeah, exactly. So here I will take x to be x1, y1, and y to be x2, y2, right? Because they are tuples. Okay, I cannot write it. I cannot write it as a real. Okay, so then what I need to check? I need to check T of
x1 plus y1 comma x2 plus y2.
No, T of x2 x1 plus x2, because if I'll add these two things, what I will get? I'll get x1, because I'm doing addition component wise. That is how we define the addition, right?
Yes, sir. Right.
So this is this, and I want to check whether this particular thing is equal to x1 plus y1 or T of x2 or y2 or not. That I want to check, right?
Yes.
So hello.
Yes, sir. Yes.
So by definition, so this is my definition of T. Okay. So by definition, what will be the value of this thing? What will be the value of T of x1 plus x2 comma y1 plus y2? What will be the value? Hello.
Sir, x. Sir, x, it will be x, sir, because T of x comma y is equal to, sorry.
T of x comma y is x. Okay. So what I'm saying, what will be the value of this particular thing?
x1, sir.
Why x1?
What is x1 plus x?
What? No. Why? What is the x?
x1?
What is
x1
the
plus x2?
1 plus x2, sir. X1
because this is the x component, right?
Yes,
I'm
sir.
taking the
Yes,
x
sir. So
component.
x1 plus x2.
Exactly. Okay. So this is
Sorry,
x.
sorry to interrupt here. How
Yeah.
we are taking like T of x plus y, we are taking two triples x1, x2. X1, y1 and x2, y2. That the second part I didn't get.
Sorry, can you repeat?
That T of x plus y, we are taking x as x1, y1 and x2, y2. Y as
No. What is the definition? Like if you go to the definition, okay. What is the definition here? We need to check sum of two elements in your domain, right? The image of the sum of two elements in the domain should be equals to the individual sum, right?
Yes.
And what is a general form of an element in R square?
Xy is a point xy.
xy. So that is what I have written. Like that is what I
No,
have written.
that I understand. But when we are taking like t of x plus y equal to 2tx plus ty is the first condition. So we are taking x as the point x1 y1 and y as the point x2 y2.
Yeah, that is what I am doing. Yeah.
So I mean, given is x1 y1, not x plus y. I mean, that is just a condition.
Sir, he's saying on the RHS it should be t of x1 plus x2 plus t of y1 plus y2, right? Now?
Okay, this one, yeah. No. This should
In the last line RHS.
x1 y1. No, what is the issue?
Sir, on the RHS, the two terms, the first term should be t of x1 plus x2 and the second term should be t of y1 plus y2.
Why?
Sir, because because x here is x1 plus x2 now and y is y1 plus y2. So and
here,
in the original definition.
No. What is x here?
Sir, we have taken it as x1 plus x2 now in the last line, sir. It represents in the last line LHS represents t of x comma y. So x would here would be x1 plus x2.
No. Okay, just let. So what is my x here? x1 y1, right? What is my y here? x2 y2, right? Hello, am I audible?
Yes, sir, you are.
Yeah, so this is my x, right? This is my y. What I need to check? I need to check t of x comma y, whether this thing is equals to t of x plus t of y or not. That is what I need to check, right? So what is x plus y here? Hello?
x1 plus x2 comma y1 plus y2.
Yeah, x1 plus
x2.
So I need to check whether this is equals to t of x. What is x here?
x1 y1. Okay, sir.
What is y here? So I need to check this, right? So I guess that is what I have written here. Is it?
Yes, sir, correct.
Yeah. So clear, right? What
yes.
I was, yeah. So the image of so this is the definition of map. T of x comma y is basically t of x comma y is x. So if I apply the same definition here, because I'm checking whether that particular map is a linear transformation or not, so I have to apply that map here. So t of x1 plus x2 comma y1 plus y2 is x1 plus x2. Similarly, what will be the value of t of x1 comma y1? Hello?
x1.
And also the value of t of x2 comma y2 is also this will be x2. So you can see, so in the left hand side you are getting x1 plus x2 and right hand side you are getting x1 plus x2. So this is true for this linear transformation. This linear transformation, the first condition, this linear transformation satisfies the first condition. Okay, let's go to the second condition. So what is the second condition? T of x is c into
c times t of x.
Okay, so what is x here? Similarly, x is
1 plus x2.
c is sorry, so what is x here?
x1 y1.
x1 y1.
Yeah, x1 y1. So I need to check whether this is equals to c into t of x1 or y1. So the left hand side, so this is what? T of x1 comma y1, and I can multiply this component wise. C. This is c of x1, c of y1. So what is the value of this? T of c of x1 and c of y1?
Cx1.
x1, sir. C into x1.
C into x1. And what is the value of this map? C into t of x1 comma y1. And you know t of x1 comma y1 is nothing but x1.
Yes, sir.
So they are equal. So this map satisfy the first condition and also satisfy the second condition. Okay. So then I can say that this map is a
Linear transformation.
linear transform. Okay, so as far as I gave a lot of example of linear transformation. Okay, so I'll give some example which is not the linear transformation, and you have to tell me why. So this is a map from T of R square to R square. Okay, so here the elements, the general form of an element is 2 tuple, and in the codomain the general form of an element is also a tuple, 2 tuple. So what is my map? Map is s comma y goes to x plus 1 and y plus 1. So you need to check. So this is, now you should do it. Okay, and some of you should explain me why this is not a linear transformation. You have to check 2 conditions, and you need to you need to check whether this map satisfies these 2, whatever condition I gave, whether this map satisfies these 2 conditions or not. If it doesn't satisfy one of them, then you can say that this is not a linear. So yeah, so your task is now you try to do it. You take like 2-3, yeah, hardly 5 minutes you take, but yeah, but do it. Check
Sir,
one by one. Yeah.
so the first condition will not
Yeah,
satisfy.
okay. Like give 2-3 more minutes. Let other also try this question. Okay, so can one of you tell why this map is not a linear transformation? Hello. Hello.
LHS and RHS differ by 1.
Yeah, that is.
It will be x1 plus x1 2 plus 1.
No, like I'm not saying what. See, the thing is, for a linear transformation, you need to satisfy. You need to check two conditions. So the question is whether they satisfy these two conditions or not. Okay.
No.
If they don't satisfy, which condition they don't satisfy? And
both conditions.
No, like for as I said, like if the linear transformation doesn't satisfy the first condition, then you don't have to go for the second condition. Okay, because linear transformation is saying it should satisfy both the condition. So if it doesn't satisfy one of them, then you can say that it's not a linear transformation. So if this map doesn't satisfy your first condition, then don't go for the second condition. From that after that itself, you can say that this is not a linear transformation. Okay, so why? So what I need to do? I need to compute x1, y1 plus x2, y2, and I need to see whether this is equals to t of so this is I'm doing addition component wise. This is this, and I need to check whether this is equals to this or not. So by definition, this is equals to 1 because I'm at, so my map is t of x comma y is x plus 1, y plus 1. I'm adding 1 in the first component, and I'm adding 1 in the second component. So here my first component is this, I'm adding 1 in the first component, and I'm also adding 1 with the second component. So if I compute this, what I should get? I should get 1, and this I should get x2 plus 1, y2 plus 1. So I want to know whether these two value they are equal or not. So if I add this, what I will get at the right hand side, I will get x1 plus x2 plus 2 and y1 plus y2 plus 2. So here I am getting x1 plus x2 plus 1, and here I am getting in the first component x1 plus x2 plus 2. So they are not equal. Okay, in some, yeah, basically in all the cases they are not equal. Okay, so you can say that this map is not a
linear transformation.
Linear transformation. You don't have to check the next condition. So I guess, yeah, I have explained yeah, a lot about linear transformation, at least how to check a linear transformation. Okay, there are so many things you need to, you can talk about linear transformation, whether the linear transformation is 1, 1 or not, whether this is on 2 or not, whether this is both 1, 1 or on 2 or not. That basically, that is in some sense it's a like what it's a functional property, like that whatever you usually do in that you did in your math 1 course, similarly you can check whether this linear transformation is 1, 1 or on 2 or not. Okay,
so can you discuss in short like isomorphism?
sorry,
I was saying that can you discuss the isomorphism topic in short?
no, short there is no point. If you don't know isomorphism, then if I will explain in short, then you cannot understand. Okay, I have to explain it properly. Okay, so my question is, if you have some idea, then you can ask me question related to isomorphism. And if you don't know isomorphism, then I cannot explain you in short. I have to go whatever, like as you told, I see that the you don't know linear transformation properly. That's why I explained from the very beginning. Okay, so the thing is, I will suggest, since now I think you can check what is linear transformation or not, right? Hello.
Yes, sir. Yes, sir.
So then I will suggest you go and check the lecture video, and after that you come and ask me, like if you have some doubt in. Okay, so before that, I'm not going. Okay, I'm not going to linear. Okay, let me, because it's already. What I'll say, it's already we are in with week 7, so I don't want to like extend it. Let me explain you at least what is 1-1 and on. Okay, so who asked this question?
Sir, me.
Okay, so the thing is, I'll explain you what is 1-1 and onto linear transformation. What is 1-1 and what is onto separately. Okay.
Sorry, sir. The linear transformation was asked by me. Isomorphism was the one which was asked by other person.
Okay. So someone asked isomorphism, some other person asked. No, I am asking who asked about the isomorphism. Are you here?
Yes, sir.
So the thing is, I will explain you what is 1-1 map, 1-1 linear transformation, and what is onto linear transformation. And actually, isomorphism is basically a linear transformation which is 1-1 and on. Okay.
Yes, sir.
That you will.
1-1 and onto.
So, but I will only explain you separately. I am not going to explain both simultaneously. Okay. Then you need to check whether. So for isomorphism, you need to check whether the linear transformation is both 1-1 or onto not. That part I'll leave it for you.
Yes,
okay.
sir. Only what how to check 1-1 and onto you can. Thank you, sir.
So okay, so first tell me, what do you mean by so when you will say a function, a map is 1-1. So for now, for the time being, forget about the linear transform. So I have a map. I have a map from domain to, sorry, this is a codomain. So when I can say that my map F is, when I can say that F is 1-1. Can you tell me the definition?
Sir, if f of x1 is some y and f of x2, f of x1 is some y1 and f of x2 is some y2, then x1 is not equal, y1 is not equal to x2, y1 is not equal to y2 implies x2 is not equal to x1.
No,
x1 is not.
No, if y1 is not equal to y2, then you are saying this should imply x1 is not equal to x2, right? Hello?
Yeah, yes, sir. That's what he told.
No. I'm asking, like, can you give me a function which is not 1-1, and I'll try to prove it using your definition. Hello?
Sorry, sir.
So give me a function which is not 1-1. Hello?
So f of x equal to x square.
Yes, sir.
F of x is equal to x square. Okay.
Yeah.
So you are saying if y1 is not equal to y2, then it should imply x1 is not equal to x2. Okay. So suppose x1 is x1 square, f of x2 is x2 square. So by your thing, first I should.
Yes, sir. Actually, there should be equal to sign instead of
x1 is equal to x square x1 is not equal to x square, that implies x1 should not equal to x2. That is true. That is true. Whatever you said, this is true for this your condition satisfy. Like if you check that condition for this particular function, this function satisfy, that implies
Yes,
this function.
there should be equal to sign. Like if x1 equals to x2, then y1 should be equal to y2. That is the thing I missed out actually.
The thing is, okay, let me tell.
But
So
sir, in case of the 1 condition that is given by him should not satisfy, right? Because f of x
that condition, that whatever definition he told is actually wrong. Okay, so so a map from a domain. So this is my domain. It's a map. So I can say f is 1 1.
Sir, can we say like all the inputs from domain are mapped to the codomain?
Yeah, that is by the definition of function. The domain should go inside the codomain. Like that is the definition of domain. Like you cannot define a function from R to R and the image of f is in C. That is not a well-defined function. So so f is 1 and when if x1 is not equal to x2, it should imply that f of x1 is not equal to f of x2. Okay, but whatever you said the reverse thing. You said f of x1 not equal to f of x2 implies that x1 is not equal to. That is true for all the function, whatever condition you gave. You told me y1 not equal to y2 implies x1 is not equal to x2. It's true for all the functions. So
yes, sir.
No, like someone asked me, is it a session for math 1? No, but the thing is, if you forget all the things from math 1, then yeah, then it can be a function from it can be a session of math 1 also. So that is the thing. I can assume all the things, but okay, then there will be no point of explaining all these things to you, because if you don't know the definition of 1 then there is no point of explaining 1 linear transformation. Okay, but I guess that is fine. So now it's clear, like this is the definition of 1 function. So this is my so similarly the same thing, a linear transformation. So you have a linear transformation from a vector space V to V1. I will say T is 1 1 if x1 is not equal to x2, it should imply T of x1 is not equal to T of x2. Okay, so but there is an advantage here. So what is the advantage? T has some property. Okay, so you don't have to check this condition. So I'll give a condition which is basically equivalent to this condition. So and I'll try to prove it why these two are equivalent. So this is the definition of 1 for T, right? That is what we define for a ordinary function, and that is the same thing for linear transformation. But I am saying I can convert, since T has some extra property, I can convert this condition to some other condition. So what is that condition? So T is 1 1 if and only if T of V is not equal to 0 for all V. Okay, I should shall I go with this definition? Just a minute, let me think. If there is this, I can say that. Okay, so T is 1 1. So okay, I'll go with that particular thing. So if and only if T of V is not equal to 0 for all V in V. Okay, see that from the condition of 1 1, you can say that T of 0 is 0, right? Because what is the condition of first condition of the linear transformation? T of V plus W is T of V, T of W. Now I will replace 0 in place of V and W. So what I will get? T of 0 plus T of 0 is equals to T of 0 plus T of 0. So 0 plus 0 is 0. So this is equals to T of 0. And this is T of 0 plus T of 0. Now I can cancel this 0 and this 0. So what I will get? T of 0 is equals to 0. So is it clear why T of 0 is 0? It's true for all the linear transformation. Hello? Hello?
Yes,
Yes,
sir.
sir.
Yeah, whoever asked this question, yeah, at least you should interact. Otherwise, yeah, I cannot explain you to some.
Yes, I'm there.
Yeah.
Sir, for T of V plus W, shouldn't it be T of 0 only? Why 0 plus 0?
No, this is the condition of linear transformation, right?
Okay.
This is the first condition of linear transformation. So for the linear transformation, T should satisfy two conditions. So this is one of these two conditions. Okay. So what I am taking, so the first condition is T of V plus W is T of V plus T of W. So what I'm taking T, V and W to be 0. So in a vector space, you will always have a 0 element. So I'm taking that 0 element. Okay. So okay, so this is a fancy way of writing 0 element, because as you can see, the 0 of R has a 0 element, that is 0, but R square has also 0 element, that is basically 0, 0. Okay, so but in general, to write a 0 element, you can use this notation, that is 0. Okay, so this is a 0 of your vector space. So my map is, if my map is from V to W, 0 is in V and 0 plus 0 should equals to, so I'm assuming this is a linear transformation, T of 0 plus T of 0, and T of 0 is basically 0. I can cancel it. Okay, so if T is a linear transformation, T of 0 is 0. So so suppose there exists, so when I can say that T is not 1 1, if so it should not satisfy this condition, right? If map doesn't satisfy this condition, then I can say that T is not 1 1. That is, there exists two element x1, x2, and they are not equal, but their images are equal. Okay, so then I can say that T is not 1 1. Suppose T is not 1, then there exist two elements in the domain V1, which is not equal to V2, but T of V1 is equals to V2, right? So if T of V1 is equals to T of V2, I have a like using the first condition, I can write T of V1 minus T of V2. This is 0. That implies T of V1 and V2 is equals to 0. And one thing you can notice that I'm assuming that V1 is not equal to V2. That implies this V1 minus V2 is not equal to 0. So what I am getting, if I am assuming that this T is not 1, 1, that is, I am assuming there exists a V1 which is not equal to V2, but their image is same. So basically what I am getting, I'm getting a, so there exists a non-zero V. So here my non-zero V is this V1 minus V2, which is non-zero, but T of V1 minus V2 is 0. So
that's why it is sufficient to check whether there exists a zero element.
No, whether there exists a V not equal to 0 such that T of V is 0. If you can check this one, then you can say that the map T is not 1. Okay, that is what we did, right?
Yes,
see,
sir.
First, see, we are not so we are in the beginning itself, we are going with the definition of the function. What I'm assuming T is not 1, 1. So this definition is from function. I'm not using something something beyond of the definition of function. What I'm trying to say, T is not 1, 1. That implies there exists two elements in the domain which are not equal, but their image is equal. But since T has some special property, using that property, I can conclude something. So what I'm concluding, I'm taking T of V1 is equals to T of V2. So I'm taking the difference, that is T of V1 minus T of V2 is equal to 0. So I can use the linearity here. That is T of V1 minus V2 is 0. But in the beginning, I assumed that they are not equal. So that implies some T of V dash. So here V dash is V1 minus V2 0, and V dash is not equal to 0. So that is in some sense they are equivalent. Like if you can find a non-zero V such that T of V is 0, that implies T is not 1, 1. And if you can't, then T is 1, 1. Okay, if you can't find such non-zero V such that the image of TV is 0, then you can say that T is 1, 1, right? And onto the same thing, for onto I cannot do anything. Like onto you have to check it. Okay, that is the same as the definition of function. Okay, there is no easy method to check on.
Sir, I have a doubt here, sir. Sir, which approach to use while finding whether a function is, or rather a vector is, or transformation is 1-to-1 or not? Like first one or second one?
See, the thing is, for the beginning, no, this method is better. This method is better. Okay, you should always try to find a V such that T of V is equal to 0. That is a better way to say that. See, there are I see after certain stage you don't have to check it. If just by looking at the linear transformation you can say that, but that requires little bit more familiarity with the subject, because there are so many theorems. Like you can easily say that whether this linear transformation, because there are this whatever you read, this dimension, all these things will play a huge role on checking all these things. But for your purpose, I will suggest you always try to check this one. You should always try to find. So this is a method to check to show that T is not 1, 1. Okay, but to show that T is 1, 1, you have to do the same way, like whatever you did in in function, like you have to go to the same procedure. Okay, to show t is not 1 1, that you can do using this. Okay, that if you can provide some non-zero v such that t of v is equal to 0, then you can say that t is not onto. Okay, I already gave you one example. I gave you this map, r square to r. So my question is whether this is a 1-1 map or not. Any answer?
So if x and y are same, then they can't be 1 1.
No. See what I said you should to prove, if you are trying to disprove it, then you should give me a element which is not 0 and image of which is 0. So
sir, any vector of the form 0 comma y will have to be mapped to 0, so it is not 1 1.
Yeah, true.
Yes,
that
sir.
is
0 comma 1, 0 comma 2, everything will map to 0.
Yeah, that is the answer I was expecting. Okay, this is 0, this is 0, but as you can see 0 1 is not 0, right? So what you are saying, you are giving one example. So what you are giving one example, one particular example where b is not 0, but the image is 0. So that's why this linear transformation is not 1. So now you take.
Sir, can you take one matrix example, sir? I am having difficulty in finding 1-to-1 in matrices actually.
Matrix, same thing. I'll do it. So let me explain a little bit more about these things. Like I'll go to the matrix. So, so next you take, suppose, r square. So as I already said, to check whether this, to check whether a linear transform is not 1 1, you should try this. Okay, but to prove this is 1 1, you have to prove it. Okay, you cannot give some example. Okay, so my map is t of So my question is whether this is 1 1 or not. Hello? Am I audible?
Yes, sir.
Yes, sir.
So the question is whether t is 1 1 or not. See what I just said now, like t is not 1 1, t is not 1 1 if there exists a non-zero v such that t of v is equal to 0, right? That is, if this happens, then you can say that t is not 1. So the question is, if you cannot find any such non-zero, then your t is 1 1, right? So what does it mean? So t is 1 1 if and only if t of 0 is 0 and t of v is non-zero for all v in V. That, so what does it mean? 0 is the only element which maps to 0, right?
Yes, sir.
See, I am saying t is not 1 1 if you cannot find a non-zero, if you can find a non-zero element which maps to 0. Okay, so t is 1 1. If you cannot find such element, that is T0 is the only element which maps to 0. So to check whether this function is 1 1 or not, we need to check, like if it is not 1 1, we can provide one example, and if it is 1 1, we have to show that 0 is the only element which maps to 0, right? So my map is r square to r square, and xy goes to 2x 2y. So suppose t of t of b is 0. If I assume that t of b is 0, and then I can show that b is 0, then my t is 1 1, right?
Yes, sir.
So suppose t of you can like you should ask, like if you are having some problem with the definition, because this is
should we check with 0 0 at
sorry
first? Should we check this 1 1 if it is 1 1 or not by taking the vector as 0 0?
No, see, 0 0 is always 0. Okay. So that is always 0. See, that is what I said. To check t is not 1 1, if you want to show that t is not 1 1, then you have to show that there exists a v which is non-zero, and the image of v is 0. Okay. Yeah. To check t is 1 1, you have to check this. If t of v is 0, that is the image is 0, then the element v should also equals to 0. If that you can show, then you can say that t is 1 1. Is it clear?
Yes, sir. But I cannot think of the approach, sir.
No, like that is what I am saying. Like you have to solve example. Yeah, please.
So in case we have to prove that t of v equal to 0, that means we can say that t of 2 t of 2 comma 2 that is 4 comma 4. No, not t of 4 comma 4, just 4 comma 4.
Sorry, I didn't.
I mean, t of 2 comma 2 is nothing but t 2 into x comma 2 into y, right? So so it will be 4 comma 4.
True.
4 comma 4, but we cannot. So and t. I mean, sorry, sir, I can.
No. What I'm saying, to check whether t is 1 1 or not, you need to assume that t. See, that is what for 1 1 you need to check if t of v is 0. That implies t v is 0. Let me explain you with an example. Then maybe it will be clearer. So suppose
sir, if I assume v to be some x1 comma y1, t of x1 comma y1. Which which translate to 2x1 comma 2y1, it should be equal to 0 comma 0.
Yeah,
then x1 equal to 0, y1 equal to 0.
Yeah, exactly. That is what I am trying to do. So suppose t of xy 0. If I can show that if xy is 0, then I am done. I can say that t is 1 1. Okay. So what is t of xy? That is 2x 2y. So if it is 0, that implies 2x is 0 and 2y is 0. That implies x is 0 and y is 0. So that implies zero. So that implies t is 1 1.
Understood.
So what I'm doing here, I'm assuming t of v is 0, then I'm showing v is 0. Then I can say that t is 1 1. To show t is not 1 1, what I am trying to say, I'm giving you a vector v which is not 0. so that T of B is T of B is 0. That implies T is not 1. So is it clear?
Yes, sir. Till the time it is of R2.
Can I ask a doubt now?
The moment it goes to matrices form, it is little.
I'll come.
But if we, in case of this second condition, we can say that T of 2, 2 is 4, 4, which also tells us that T is 1, 1. Can we say that?
Sorry?
T of 2, 2 gives us a vector 4, 4. So here we can clearly see that when V is not equal to 0, T of V is also not equal to 0.
That is basically the contrapositive of this statement.
Yeah.
Whatever you are saying,
yeah,
you are basically saying the contrapositive of this statement.
Yes. Can we draw to the conclusion of 1, 1 using that?
Yeah. If B is not 0, then T of B is not 0.
Okay.
Okay. That is, see, if the contrapositive is true, then this statement is, then your statement. If contrapositive of a statement is true, if this is true, then this is true. If statement is true, then this contrapositive should be true.
Okay.
That is if and only. You basically you are saying the contrapositive.
Yes, sir. Just the opposite. Yeah. I am using the opposite logic.
So whoever said like matrix, that is actually, see, one thing, like I don't know, like most of you are facing problem. I like many of you told like you are comfortable with week 5. So I don't know, then you should not actually, because see, the whatever we are doing now is in some sense the consequence of week 5. We are, all whatever we are doing is just the application of Gaussian elimination. Okay, like most of the thing. Okay, to check dimension, to check like this basis and whatever, to see whether like to know the rank and nullity, whatever is there. Just some sense we are doing Gaussian elimination. Okay. Anyway, so now you take this example. X minus y and x. So my first question is whether T is a linear transformation or not. So the first question is, first we need to check whether T is a linear transformation, and what is your answer? So yeah, any guess?
First condition is okay.
Yeah. Second condition, yeah, you can see that it will be okay. Like if you multiply C, then you can take C out of that. Yeah, second condition is also okay, like because T of Cx Cy is Cx minus Cy and Cx, and which is nothing but C into x minus y x, which is C into T of.
Second is also okay.
Yeah. So yeah, it's like whoever solved it is fine. Otherwise, you try to go with the same procedure whatever I have told you. Okay, you go one by one. You can complete it. So the thing is T is a linear transformation. So this map is a so the next question is whether T is 1 1 or not.
Yes, sir. T is 1 1.
Why?
Because if we take T of x comma y equal to 0 comma 0.
Yeah, perfect. Yeah, T of x comma y is equals to 0 comma 0.
Then we can also say that x minus y comma x equal to 0 comma 0.
That implies x is equal to 0.
X equal to 0. Y equal to 0.
X minus y equal to 0, and you substitute, you will get y is equal to also 0.
Yeah.
So then you can say that T is 1 1.
1 1.
So yeah. So okay, so let's go to a example which involves matrix. So suppose my linear, this is my map. Okay, let me take you some specific matrix. 1 2 2 3. See, like someone asked me related to this, like to matrix question. Are you here? Hello.
Yes, sir. I am here, sir.
So are you searching for this kind of example?
Yes, sir. I am getting stuck actually. I'm equating to 0, but somewhere in between.
Then see, when you are equating it to 0, then basically you are solving a Gaussian. Then you have to go through the Gaussian process. Okay, let me explain you why.
Yes, sir. I'm doing something like Ax is equal to 0.
So see, this is basically what, if you multiply this is basically what this is in some sense you can write it as x1 plus 2x2 and 2x1 plus 3x2. Like you can write it in the column.
Yes, sir. I'm equating these two equations to 0, two expressions to 0, and trying to find whether x1 is equal to 0 or x2 is equal to 0.
So now let's do it.
Is that sufficient?
Yeah, that is what, see, that is what you do. See, the thing is this is the simplest way to do it. Okay, so otherwise you can check with this matrix. Is if the determinant of the matrix is non-zero, then you know it cannot have non-trivial solution, right?
Okay, understood.
So what you are searching here? So you are searching. So you are taking T of x to be 0. You are trying to find the solution of this system, right?
Yes, sir.
That implies what? That implies your matrix A into x is equal to 0, right?
Okay, so if I find whether A's determinant is 0 or not,
if the determinant of A is not 0, then A is invertible, right?
Yes.
Then you can multiply A inverse both the sides. So then you will get x to be 0. So that basically what you are getting, T of x is 0 implies x is 0. So that implies T is 1 1. If determinant is non-zero, okay. If determinant is 0, then yeah, then obviously you will have if it is a square matrix, then obviously you will have a non-zero solution. Two participant raised hand, like who? Any question? Like two of you actually raised your hand.
Yes, sir. This is Kaushik. Can you hear me?
Yes.
Sir, I have a question regarding the spanning set and concepts explained in activity question 7.1.
Do you have some specific question?
Yes. So can you please explain what is the spanning set?
Like as I said in the last session, Subhajit explained it properly.
Okay, I'll refer to that then.
Yeah. You go and watch the video of the last session. Okay, now actually I'm trying to explain something about linear transform. So
if the determinant is non-zero, so what are you concluding there? Like,
so what
is it 1-1?
No, it's 1-1. Yeah.
Okay, so in that case, we can check directly.
Yeah, you can check
date
directly.
is non-zero.
Yeah, if date is non-zero, then you can say that. See, what is your so for linear transformation, what you are checking? 2, 1, 1. If t of x is equal to 0, then it should imply that x is 0.
Sir, but this is applicable only for a square matrix.
Exactly, because you can compute the determinant only for a square matrix. You cannot compute the determinant of a non-square matrix.
Correct,
Right?
sir. If it is a non-square matrix, then Gaussian elimination.
Then you have to go through the Gaussian elimination. You don't have any other choice.
Okay,
if it
then,
is
then all the variables should be independent in that.
Yeah, because see, suppose you have a map from something
also
called.
Sir, in that case, if there are 3 rows and 4 columns, suppose.
Yeah, suppose
so
I can suppose I am
R2 to R3.
R2 to
yeah.
R3.
So we can write it like x comma y. Yes, x comma y comma z.
Suppose this is your system. Y plus z. Sorry, this cannot be y plus z because there is no z. So 2y plus x, maybe some 3x plus 1. So to check whether t is 1, 1, what you need to check? When t of xy is equal to 0. So this is equivalent to x plus y equal to 0, 2y plus x equal to 0, 3x plus y equal to 0. Now you need to check the solution of this system, and that you can do using Gaussian elimination. Okay, if that system has a non-trivial solution, then you can say that t is not 1, 1. If the system has trivial solution, then you can say that t is 1, 1. Is it clear?
Sir, please repeat that part because I thought it is non-trivial, then it is 1, 1.
No. If this system has trivial solution, okay, that is x is equal to 0, y equal to 0, and z x. Okay. Then
all the 3 should be 0. Okay.
Yeah. Then no. There are no 3 variables here. There are only 2 variables. If this particular, so this is a system, right? If the system has only one solution, that is 0, 0, because the system is homogeneous. Okay, then you can say that t is 1, 1. But if somehow you manage to show that the system has a non-trivial solution, that is you have x comma y which is not equal to 0, 0, but this satisfies this system, then you can say that your map T is not 1, 1.
Sir, in Gaussian form, Gaussian elimination form, how will this get reflected? Like 1, 0, 0, 0, 0, 0, 0. Some one row becomes full zeros. Then there is a dependency on others. Something like that, sir. In that case, it will called as non-trivial solution.
No, sorry. No, the thing is when like it's depend on the number of dependent variable and independent variable. How you actually are getting. Okay.
Correct, sir. What I mean to say is if we get all our independent variables, then we solve it. That means in this system, it will be 0, 0, obviously.
Exactly.
So at least if one variable becomes dependent, that means it is non-trivial.
Yes. That is the same thing as saying whatever I said, you are saying.
Understood.
Yeah.
Understood. Now it's clear, sir.
Yeah. So
can you please once again generalize the concept when determinant is 0 and then it
sorry. Like I cannot hear you. Okay.
Yes, sir.
No. Can you repeat? Hello.
Sir, I just want to say, can you please generalize? It means can you put a final statement for when the determinant is 0 So at that time, the solution is 1-to-1 and trivial, because I'm confused between this trivial and determinant.
Okay, can someone else repeat her statement? Like actually, I cannot hear like what actually she is trying to say. Hello.
Sir, I think she's saying you to explain what you have said in gist, like when you should use determinant, how you should use determinant. If you cannot use determinant, what should you do in general?
I just want a final statement for, like, if determinant is 0, then the solution is trivial or the solution is 1-to-1. Means a final, only the conclusive statement.
So if the determinant is non-zero, then this whatever system you are getting here, this system will have will have only trivial solution. That implies your t is 1-1. Okay, and if your system has if the determinant is 0, then the system will have a non-trivial solution, and that's why the linear transformation cannot be 1-1. But someone pointed out, since we sometimes we may get a matrix which is not may not be a square matrix. So if the matrix is not square, then we cannot talk about determinant. Okay, so for that, what you need to do, you need to apply the Gauss elimination method to check. You have to apply the Gauss elimination method, and you have to find out the solution of that system. It doesn't matter, it's 2 variable, 3 variable, 4 variable, you can apply it.
Sir, in the system that you just shown us, in this system, what I am getting is a matrix which is 1, 0, 0, 1, and 0, 0. I am telling this row wise. So
1, 0,
1, 0, 0, 1, and 0.
0?
0. So this is what I'm getting.
This is so you are getting 2
dependent
variable. So that implies your system has only trivial solution, right?
Sir.
Hello.
But in the third row, here only 2 variables, no, sir. There is no use of the third row here.
No, like this. What is the matrix associated with this system?
This will be 1, 1, 2, 1, and 1, 2, and 3, 1.
So then when you will compute the
I think it will be 1, 2, because the 2
yes, sir, second row is 1, 2.
Oh, sorry, yeah. So then when you will compute the row reduced echelon form, then you should get a similar matrix, right? Similar kind of matrix. The order should be same. So you should get something here in the third row.
What does it signify, sir? If I get third row as zeros, that's what is my question.
No, the third, see, in a homogeneous system, okay, that is not a issue. If your system is non-homogeneous, then it may create a problem. If your third row is 0, because see what basically you are doing, your system. So this is your system, right? This is the matrix associate with the system. And what is your B here? B is you are solving for 0, 0, 0, right? When you will write the augmented matrix 1, 1, 0, 1, 2, 0, 3, 1, 0. So when you will do elementary row operation, all the element in the third column, it will also 0, because all the elements in the third columns are 0. That's why we are neglecting this when we are trying to solve a homogeneous system.
Oh, okay, sir. Understood. But actually, if it was some value over the right side, then it would have been problem.
Yeah, then because when you will do elementary row operation, then the value will change, right? Okay, but so since here we have only 0, and you add 0 with 0, you multiply 0 with you are going to get 0. That's why we are neglecting it. But when the right hand here, this part is when non-zero, you cannot neglect it. You have to write it. So if after, suppose your right hand side is non-zero, and in the end you are getting 0, 0, 2. Okay, then the system cannot have solution. Okay.
Yeah, no solutions.
Yeah, cannot have any solution. Yeah, that is the thing. Since we are dealing with a homogeneous system, so we don't care about this part. Okay. But when you are so for for to check 1, 2, I guess, suppose you want to say that this there is a element in, there is some ABC.
So we can say that this is the 1-1 linear transformation.
Yeah. Because it's clear that this is.
That means if it does not have any independent variable, it signifies that it is an 1-1 linear transformation.
Exactly. Same thing. Like, see, you are basically solving the system, right? And the way you solved a system in week 5 using Gauss elimination method, you have to use the same method. Okay.
But
no difference. So is it clear?
Yes, sir.
Yes, sir.
Okay. So any other thing you want me to
can
explain?
I ask one thing from the nullity?
Nullity, yeah, please.
So one thing that I saw while solving a question today is that we need to to solve to find out the nullity of a matrix. We need to have the row echelon form, right? Not the reduced row echelon, only the row echelon.
No, sorry, I didn't get you. Like, you were saying to find out the nullity
of the nullity of a matrix. We need to find the row echelon form of that matrix.
Row echelon form of that matrix.
Yeah, row echelon form of that matrix. So what I am trying to say is that today while solving, I found that there are 2 row echelon forms.
Row reduced echelon form and row echelon form. There are two.
But row reduced echelon form is is unique for any matrix, right? But row echelon form is not unique.
Yeah, maybe. Yeah, I have to like think whether it's unique or not. But certainly, row reduced echelon form is unique for a matrix. Yeah.
So, I mean.
Sorry, what is the issue?
The issue is that today while solving a matrix, in some step I reduced the matrix to row echelon form, and still I was getting 2 independent variables. But after another 1 or 2 row elementary operation, I got only 1 independent variable. So my question is that
you should check the dependent and independent variable in the end, right? How?
In the end, that is what I am going to ask. That what is the end? End is row echelon form, right?
The thing is it's up to you what you want. Okay. So, the thing is, if you think you can get the solution from row echelon form, then there is no point of going into row reduced echelon form.
Yeah.
Okay. So it's up to you what actually you are trying to find. Okay. So if you think that, okay, I have reached this stage, and from this stage I can get the solution easily, then why you will go to, like, suppose you got something, suppose you got something like this: 2 0 0 0 5 0 0 0 7. Why you will multiply 2 here? Okay, no point, right? From this system you can say anything about the solution of the corresponding system of linear regression. So you don't have to go for a row reduced echelon form. So that is the thing. It's up to up
what
to
I am
hmm.
trying to say is that
Hmm.
I mean, can I just tell you the matrix that I got?
Yeah, please.
Yeah. So the matrix is, I am saying this row, right? 2 0 minus 1 0.
Just a minute. 2 0
minus 1 0.
2 0 minus 1 0.
Second row is 0 2 minus 1 2.
0 2 minus 1
2.
2.
And the third row is 0 0 1 minus 1.
0 0 1 minus 1.
Minus 1. So now if you perform one or two row elementary operation, okay, you will find another matrix which is 1 0 0 minus half.
Okay, you are saying if you perform some more, okay,
Yeah.
tell what you will get?
1 0 0 minus half.
Minus half.
Then you will second row is 0 1 0 half. Third row is 0 0 1 minus 1. So now what I'm trying to say is that let's say if I in the first matrix, if I divide the row 1 and row 2 by 2, then also I am getting a row echelon form. And in the second matrix also I am getting a row echelon form. But in the first matrix I am getting the nullity to be 2 because I am getting two independent variables, that is x3 and x4.
No, in the first you are getting 3 independent variables.
X4, the last column, X4 is 1 and the second last column, X3 is 1.
No, here 2 2 1, right?
Yeah.
Here you are getting 3. And here also you are getting 3.
Three non-zero rows, right? So
yeah. No,
these are the dependent variables.
These are dependent variable, yeah.
So in the first matrix, which are the independent variables? Then? I mean, -1 is one independent variable, and
this one is basically independent variable.
Which one? Can you mark it?
Yeah, I marked it, right? This one. This particular, the fourth row, there is no pivot in the fourth row, right? That's why this is a independent variable. Whereas you have pivot here, and pivot here. Okay. But in this row, in the last column, in the first matrix, you don't have pivot. So that's why one independent variable in the first matrix. Similarly, in the second matrix, you have one independent variable.
Then my concept of
Can you please explain this pivot element in this, like how it is independent?
Like this, I already explained in one of the live sessions. So
today or sometime else?
In week 5. Yeah, you can watch week 5.
My concept of independent variable is not clear. Then,
no, the thing is, yeah. Please go into. I explained it properly. Like I took one example.
I will watch.
Yeah, you watch. Like if you have some problem, I can explain it again. But yeah.
So what date is it?
That's certainly difficult to say. But as far as I know,
approximately.
In week 5, so when the week 5 content released, okay. From week 5 to week 6, right? There are 3 live sessions. Okay. So one of them actually, as far as I remember, I completely explained to someone and what is independent variable, what is dependent variable, with 2 examples as far as I remember. So,
sir, I have a suggestion regarding that, sir. Already the links to old sessions are available on the portal. One on remarks column or somewhere you can mention the topics which were discussed during that session. That would be helpful for us to directly go to that.
Okay, yeah, that is certainly a great idea. Okay, like the thing is, yeah, certainly we can say the thing is we can do it.
Because already you are posting the links, sir. Just that it has to be mentioned, like what all major topics were discussed.
Yeah, it's true. It's true. Yeah, we'll do it. Yeah, certainly it's a good idea. Okay, because unnecessary, otherwise you have to. Yeah, it's not looks good to that you should go and check all the live session where actually I explained what. So yeah, we'll do it. Okay, at least I can say that we'll do it for week 6. Okay, because I also don't remember what I did in the first week. So for that I have to watch it. Okay, so still we'll try to complete it. Like yeah, we'll try to complete. We'll try to post it in a complete format. Yeah.
Yes,
Yeah,
sir.
but
At
yeah,
least from today's session onwards,
yeah,
you can post.
Definitely. Yeah.
And sir, another question in the practice assignment. Question is okay. I am okay with the question, but I saw the solve and I am a bit confused in that.
No, week 7 or what?
Week 7.
Have you checked the solution?
Yeah. I checked the solution and I got confused in the solution only. I don't think this is a very big problem.
Sorry.
It's a very small. I mean,
Yeah. It doesn't matter. Like you, what is the issue? Yeah. What is your question?
The question is that here we can see that they are taking each element and they are trying to equate the coefficient. So if I take O2 as the oxygen as the element, then I can say that X2 2X2 equal to.
Okay, I like to understand your question. I have to check. Like, can you tell me which question you are talking about? Activity.
First question, practice assignment. First question.
Okay, before that, you check the solution.
Sir, one of the statements. I got 3 equations. I only got
practice. There is a solution for practice assignment.
Yeah, I saw the solution.
Okay. So
I got confused in one equation.
Yeah. Please. Oh, in question number 1, right?
In question number 1.
Yeah.
One equation I got confused. Rest of the.
Yeah. Please.
So you can see that they are equating for the oxygen. So they are telling that X2 is 2X2 is equal to X3 plus 2. Sorry, 2X3 plus
X4. Yeah.
2X3 plus X4. They are saying. But what I am saying is that the equation will be X3 equal to X3 plus 2X4.
X3 plus 2X2.
So which is correct? I mean, according to the logic, if you can just.
No, you are getting 3 equations, right? What is your first equation?
One equation is for carbon dioxide. Carbon. One equation is for carbon. Another equation is for hydrogen, and the third equation is for oxygen.
Oxygen. That is what you are saying, that there is some mistake
they may be wrong. Yeah.
So for the oxygen, okay, let me check it for oxygen. Okay, certainly there can be a mistake, and yeah. No. I myself prepared the solution, so there can be a mistake.
Sorry, sir, I am not trying to point out the mistake. I am just trying to understand the logic, sir.
No. First of all, there is no problem if you are trying to point out the mistake. That is perfectly fine, and that you should do. Then only you can learn. Okay, so for oxygen, I am getting 2X2, which is equals to 2X3, which is equals plus 2X4.
Yeah. So there. Yeah.
So okay, in the left hand side, okay, in the left hand side you have 2 oxygen atom, right? And you have X2. So from there you are getting 2X2.
2X2. Yeah.
From the right hand side, you have in the first in X3 CO2, you have 2 oxygen atoms. Okay. And coefficient is X3. From there, you are getting 2X3, right? Hello?
Yeah.
And after that, what you have? You have X4 H2O. And here you have only single oxygen atom. So from there, you are getting X4, right? So then the equation should be 2X2 is equals to 2X3 plus X4, right? Hello?
Okay.
I guess that is what I have written. Yeah. Sorry.
I understood, sir.
You got my point, right?
Yes.
See, yeah. So because coefficient of X4 cannot be 2, because here the number of carbon atoms in H2O is 1. Okay. Number of carbon atoms in CO2 is 2. That's why you're getting 2X3. Number of atoms, oxygen atom in O2 is 2. So that's why you're getting 2X2, which is equals to 2X3 plus X4. Is it clear now?
Yes, sir. Yes, sir.
Okay, fine.
Sir, I think I missed out something on onto, like the way you have explained one-to-one, that onto discussion, I don't know. We digressed from there.
No, I didn't discuss about onto. Like onto, as I said, onto there is no method for onto. Like you have to either you can do it directly, or you have to say same thing. You have to.
Sir, it's like instead of equating to some 0, 0, I equate to some AB or something.
AB, and you have to show that this has a solution for all possible AB. Okay, that is basically onto.
That means the solution need to be unique in that case also, sir?
No. For onto it, no. If you want your linear transformation to be both 1 and onto, then certainly it has to be unique. Okay.
That means we need to find whether one is homogeneous equation should have a trivial solution, and normal equation should have a unique solution.
No, see, the thing is, that is what I am saying. If you are only trying to find out whether your linear transformation is onto, okay, then you don't have to go for uniqueness. Only one solution suffices to the fact that your linear transformation is onto. Okay, but when you are checking both 1, 1 and onto, okay, then you have to keep in mind that the solution has to be unique. Okay.
Got it, sir.
No, and one more thing. So if you can say that you are taking A comma B, and that solution for all the possible value of A, B, the solution is unique, then that particular thing implies that your linear transformation is 1, 1. You don't have to do it for homogeneous, because when you are taking all the possible values of A comma B, then 0 comma 0 also comes under that assumption.
That means if I do A comma B and I get unique, it implies both 1, 1 and as well as onto.
No, it implies, yeah, true. This implies this is 1, 1 and onto.
Sir, can you explain the practice assignment question 5 option 4? I can.
Which one? Practice assignment?
Question 5 option 4. And I have seen the solution, but I cannot understand.
Yeah. Question 5. Okay, if the rank of a matrix is 3, then there exists one vector corresponding to one column, which can be expressed as a linear combination of the vector corresponding to each of the remaining column. Okay, so this okay.
The option and
okay, so your question, okay, so matrix is 4 cross 4, right?
Yes.
So, but what you are getting rank to be 3. Rank is 3, right?
Option 1, 2, 4, sir.
Okay, 4 you are saying. Okay, option 4. Question number 5, option 4, right? If the rank of a matrix is 2, then the dimension of the vector space spanned by the vector corresponding to is column must be 2. That is a fact, right?
Can you please explain what is written in the option?
No, you are okay. Let me first confirm. You are talking about option 4, right?
Option 4,
yeah. So you know rank that for a matrix, row space and column space, they have same dimension. Huh? So then it's just a consequence of that, right?
The dimension spanned by the
row space
will be equal to the dimension spanned by the
column space. So this is a 4x4 matrix. It's given that the rank of the matrix is 2. So that implies the dimension of the space spanned by the row vector of the matrix is 2. Right?
Yeah.
So that implies, since we are using that rank row space, column space, they have same dimension, then from that you can say that the dimension of the space spanned by the column vectors of A is also 2.
But in case of calculating the column space, should we do it in different process, or should we conclude that from the same matrix? Let's say I am getting a matrix, I am getting a Gaussian matrix of 1 0 1, 0 1 minus 1, and 0 0 0. Third row is 0 0 0. So here we can say that the row dimension, dimension of the row space is 2, and the column space is 3, right?
Okay, 1 minute. I will share my screen. It's better to write whatever you're saying. So what I'm okay. Let me tell you. Okay, repeat your matrix here.
1 0 1.
1 0 1.
0 1 minus 1.
0 1 minus 1. This is your matrix.
0 1 minus 1. Second row will be 0 1 minus 1. First column it is 0. Second column it is 1. Then it is minus 1.
Right.
Yes, sir. Yes, sir. Third column is 0 0.
Third column is 0 0 1.
0 0 0.
0. Okay, then it's not an issue.
Not necessary.
So my point is, you take the row space. So the row space is what? Span of 1 0 1 0 1 minus 1. This is your row space. And what is your column space?
1 0 0 0 1. Sir, I got it.
What I am trying to say, that see, row space and column space, they can be different, okay, but their dimension is always same. You got my point? Yes. The dimension of row space is equals to the dimension of, okay, let me tell you, this is a very important fact. Don't forget it. Like it's really important. You can use it in lot of places. Like even in the upcoming week, you will see the power of this. Like in many places, you can say like when that is what I was explaining in the beginning. Like by looking at the linear transformation, you can say that when a linear transformation is 1 1 or 1 2. So this is basically column space. They are same. The space, they may not be different. They may be different, but the dimension is always same. Okay. From that, you can say that the option 4 is true. Is it clear?
Yes, sir.
Okay. Okay. Any other doubt? Hello? Hello? Okay. So shall I close the session then?
And one small thing, sir.
Yeah, please.
That in case of question number 6, when it is saying find the dimension of the vector space, that means we are considering the whole matrix to be a vector space.
Question number 6.
Yes, sir. Practice result.
You are considering, no, this is not whole. See, a matrix cannot be a vector space. Vector space is a collection of huge number of matrix, infinite number of matrix. Okay, matrix and vector space, they are different. Vector space contains a matrix. Okay, vector space
contains a matrix. Yeah.
Contains infinitely many matrix.
Yeah.
Okay, but a single matrix cannot be vector space.
Yeah, but what I'm trying to say is that we have seen in case of many vectors, like if there are 3 vectors, we can write 3 vectors of R3. We can write those vectors as a matrix form in the matrix form.
But R square contains infinitely many two tuples. Okay. Yeah, that is what I am trying to say. That a single matrix doesn't represent a vector space.
No, I'm not saying that. What I'm trying to maybe I cannot explain it properly. What I'm trying to say is that in case of I mean, I got that the dimension of this vector space will be 2 into 3. That will be 6. I got that. What I didn't get is that let's say we have a vector space. We have a subspace of a vector subspace of V, which has 3 vectors, V1, V2, and V3, and all these 3 vectors belong to the R3. I mean, these are all 3-dimensional vectors.
Which one? In question number 6?
I am just giving an example.
Okay, yeah, 3-dimensional. Yeah, sorry.
Yeah, R3. All these vectors belong to R3. Then we can write all these vectors in the form of matrix.
Yeah, true.
Yeah. So then that matrix is explaining something else, and the matrix that you gave in this question is explaining something else, right?
Yeah, true.
I mean, that matrix, the dimension of that matrix will be 3. But in case, right? Am I correct, sir?
Dimension in the sense spanned by the
spanned by the vectors.
Yeah, better you say row space and column space is better, because dimension you can use for matrix and also you can use for a vector space. Yeah.
So let's say the row space of that matrix will be 3. The matrix that I gave and the matrix that you gave, the row space of this matrix will be 6. So these two are different.
Yeah, certainly they are different, because see, the thing is this is a vector space that see, when you are taking a particular matrix, we are talking about that matrix. Okay, but when you are talking about a vector space, you are talking about you're talking about the infinitely many matrix in that vector space.
Infinitely many matrix which are of the form 2 cross 3.
Yeah, 2 cross 3. Yeah, but when you are picking one element, you can pick one element from that vector space and you can talk about null space, column space
of that
particular matrix. That is different, and this vector space is different.
This vector space is different. In this case, the span, it will span in all the 6 what to say, R6.
Yeah. Priyanshu Singh, are you here?
Yes, sir.
Yeah.
Sir, I had a doubt in the first lecture of the 7th week, so where they told about the ranking of a matrix for the where they have to find the ranking. So, sir, there they told that when we use the row values, the vector as a row for the matrix, then when we lead to the after the Gaussian transformation, when we lead to a final value, so then we wherever the values are present, that we take as a that we take as our basis. But for the same vectors, when we take it in the form of columns, we
in row you cannot do that, but for column you can do that.
So because in column it was written that in column we had to, after finding the Gaussian transformation, whichever rows are there, we have to go back and see the original one vector, and we have to take that as the basis.
Corresponding original, whatever set you took. Yeah, true.
So why in rows we have to take the final product as the basis, and why in column we have to take the original one as the basis?
No, in the problem with the row, you can do with the row also. But what is the problem with row? In row, actually, you are changing the row. Okay. So suppose, let me give you with a let me explain with an example. Okay. So are you here, Sriyanshu? Hello.
Yes,
Hello.
sir, yes, sir.
Yeah. Just a minute. Okay, so the thing is, suppose this is my space 1 0 0 and 0 0 0 1 0 sorry 0 0 1. Okay, so the thing is, when you will take it in the form of rows, what you are getting? 1 0 0 0 0 0 0 1 0, right? But this is not in row reduced echelon form. You have to change it.
Yes, sir.
1 0 0 0 1 0 0 0 1. So now what is the problem? Now if you take the first row, so you have two row with two non-zero row, right? The first row and the second row. Okay.
Yeah.
But if you take the first row and the second row, they don't span the space spanned by this.
Yeah.
Because in row reduced echelon form, what you are doing, you are interchanging the row. Okay, so that you have to remember. Okay, then you can take it. Okay, if you can remember, now you are changing second row with third row and third row with the second row. That you have to do here. You have to change the second element in your original set with the third element and third element with the second element. Then you can say that, okay, since you have changed the set, from 1 0 0 0 1 0 0 0 0. Why you change the set? Because you changed the two rows here. Okay, then you can say that since the first two row are non-zero, then you can say that this first two element will span the space. That you can say, but to use it, you have.
So this is the case where the second column is not having any value. That's why we replace it. But if the second column was like having a value already, then we can take the original one, or take the
now I'm talking about row method. I'm not talking.
That's what I'm saying about row only. Like here, you have taken the particular example, like 0 0 0 0 is the second row.
No,
that's why we have to interchange it.
Yeah, that is why I am saying that you cannot say that the corresponding element in the first in your original set, they will span the space. That, see, one example is enough to contradict one fact. That is what I am trying to say.
So in column, there can be a case where the second column is not there, so we have to interchange it.
No, because when you are doing row reduced echelon form in a column, okay, then you are not interchanging the column, you are interchanging the row. Okay. When you are doing, so then you don't have to remember that fact whether you are changing the columns or not, because if you are applying row reduced echelon form to columns, then you are basically not interchanging the columns. Okay, one thing is, it's not a proof. Okay, the proof requires, if you want a rigorous proof, then it requires elementary matrices. Okay, it's kind of straightforward from elementary matrices. Like,
okay, sir, got it, sir.
Yeah.
Sir, just one more doubt. Can you just tell a brief about the spanning set? Like other than being independent, what one more condition we have to find for it?
Okay, I told this 2-3 times in the last session video. Okay, Subhajit actually explained it everything in that video. This Friday live session. In Friday lesson,
Okay.
he explained it, and you can see it in the portal or maybe.
Okay.
Yeah. Okay. Okay, let me then stop the session. Okay.